Thank you very much indeed, Professor Tamura. Quite stimulating. Can I remind people, if they have questions or comments to make to Professor Tamura, could you please use the chat function to do so? Could I ask Professor Tamura to stop sharing his screen now so we can move on to the next speaker? The first of the two short presentations, is given by Professor Forrest Masters, who's a professor in the Engineering School of Sustainable Infrastructure and Environment, and he serves as an Associate Dean for Research and Facilities in the College of Engineering. He gained his PhD in Civil Engineering, Structural Engineering from the University of Florida in 2004, and he's received support from more than 50 grants from state, federal and private sources, including the NSF Career and MRI programs. He leads one of 7 natural hazards engineering research infrastructure facilities for the NSF to study the damaging effects of extreme winds on civil infrastructure. He's published more than 100 papers in peer-reviewed journals and conference proceedings, and has given more than 100 invited presentations. He serves on the board of the Federal Alliance for Safe Homes and recently served on the NIST National Advisory Committee on Windstorm Impact Reduction. In 2014, Dr. Masters was awarded the Junior International Association of Wind Engineering Award, which is the highest award in his field that recognizes significant and original contributions to research by an individual under the age of 40. He was also honored with the Outstanding Achievement Award in Mitigation at the National Hurricane Conference. So I hand over now to Professor Masters, whose presentation is entitled Revisiting Hurricane Maria's Impact to Puerto Rico, Topographic Wind Speed Up in Complex Terrain. Thank you, Forrest. Over to you.
Thank you so much, Chris. It's really a pleasure to be here. If I can take a second for all of us just to pause and reflect what we've been through the last year and a half. And I know many of us have faced a lot of challenges, both personally and professionally. For me, I take a lot of comfort in knowing that there is this international community of wind engineers and scientists, that you're all out there. So I'm happy, I couldn't be more happy to be here to share some work that we've been doing lately with you. The first thing I'd like to do, I'd like to acknowledge 2 people that are on the Zoom with us today. Jorge Santiago is our PhD student on this project, and Luisa Ponte from UPRM, who's also joining us. So we're going to talk about Hurricane Maria and some ongoing work in that area. So I'll quickly move through the motivation for this work. I'll talk about several projects that are underway. We actually have a total of 3 projects that are going on, but one of those is embargoed. So I'm not really in a position to talk about that, but I can talk about the other 2. And that's the FEMA STAR 2 project, which we finished, and then something called the EAGER project. And then I'll give some insights on this whole process. In fact, those of you that know me are probably wondering why is Forrest talking about topography? The real answer is that's certainly not something I was doing a few years ago. It's something that came out of the blue, and but we fully embraced. So with regards to Hurricane Maria, it was truly catastrophic. I mean, Category 4 storm at landfall. It was the worst storm in 80 years for the country. Over 3,000 people killed directly from the event, but there have been subsequent studies that's shown a lot more people died for, because of indirect causes. Damage estimates over 100 billion, and truly the country is still recovering. It was an absolute tragedy. One of the interesting things about Puerto Rico is the fact that it's in this mountainous region, and in fact, so much so when we think about the wind intensity in the surface wind field, it's even specifically called out in the Saffir-Simpson hurricane wind field as being sort of a special wind region where the winds can be a lot higher, and that's absolutely the case. As you can see here, we're looking at Hurricane Maria's track over the island, and you can see the full passage. And you can see there was almost, around 650 meters of elevation change as the storm moved through the area. And as you can see from the terrain profile, it's not a collection of nice sinusoidal hills. Puerto Rico is located basically at the boundary of two tectonic plates. And you have a pretty large region of mountains that runs through the middle of the island. So it makes for some interesting terrains. And as a result, and this is not the first storm this has happened, topography was implicated as a damage driver, causing flow accelerations on ridges, escarpments, tops of different landforms. It was both observed back in Hurricane Georges, actually in 1999. You can see a picture there on the left. And then also here in Maria, you can see this is one of the field assessment teams that the universities lead. It's called the RAPID program, led by Tracy Kajusik at Notre Dame, as well as working with the FEMA mitigation assessment team. So that implication is supported thoroughly in the literature. We know that wind speed ups can reach a value of 2. Looking at flow upwind of the transition up the slope to the top of the hill or the mountain. Well, what's really interesting is if you look at this literature, which has been going on for decades. I mean, there have been high quality projects that have been occurring since the 40s and 50s even on this, but a lot of them focused on simple studies. I mean, simple landforms rather. So probably many of you are familiar with like the Askervane project and others that have taken place over the years. I would say I'm not going to get into field experimentation today, but in addition to the experimental work, done in the laboratory, quite a few projects, even some done recently in Portugal and other places, to go in and quantify the fluxes and surface behavior, looking at canopy flows, kind of the whole 9 yards, and that's informed our understanding of modeling. But when we think about complex topography, which is really what we're after here, really only a handful of studies that have been done over the years, working directly from digital elevation data, putting real, environment, in a wind tunnel for physical modeling. So if you're looking for a nice summary of some of this, there's a great paper by Finnegan that just came out that covers a lot of this. So yeah, the research certainly supports it. And I didn't even get into the numerical stuff. I'm really talking about experimental, strong wind type conditions. So as a result, when the FEMA mitigation assessment teams, finished up and produced their conclusions, it was determined there needed to be a special wind map generated for, a special wind region map generated for Puerto Rico. And just kind of like what had been done following Iniki in Hawaii in that area. And so this is sometimes referred to as microzoning, but basically a special wind map. So rather than looking up, say, KZ in AC7, you can work directly off the map to pull wind speeds. And so FEMA and its contractors, through a program called STAR2, which involves a couple different engineering firms, including Atkins, worked with Applied Research Associates with Peter Vickery to develop that map. And they came to us and asked us to do a project to collect data to validate the modeling, semi-empirical modeling that Peter was doing. And so we got involved. It was an interesting project because we didn't have a lot of time. We were not equipped in our lab to do any type of topography work. I think they got a hold of us in May and we had to start by June. And we only had, I think, 3 months to do the whole project. As you'll see, it turned out to be, I think, one of the largest topographic studies ever completed. The project centered on 6 study regions on the main island, basically at the landfall point in the areas, Yabacoa and Humacao regions, and then also inland, very built up areas there in the mountain chains in Utuado and Ayabenito, and then also the 2 municipal islands, Culebra and Vieques. So we picked those regions to work in to get some type of representative sampling of the area. The island's just simply too large to, to put in the wind tunnel. So we ended up working with a 1 to 3,100 scale, which is nominally the size you need to encompass most of Culebra. And that's nominally a 12.2 kilometer diameter and a projected state plane coordinate system. So as I mentioned before, this is real terrain, real environment. It looks something like this. Here we're looking inland, I think at Ayabenito or maybe Utuado. But you can see our measurement cruciforms where we plan to do data collection, and you can see all the different locations, which in plan form are spread equally, but when you look at it obliquely like this, it does look a little bit funny. So we developed 6 4-meter diameter models. We took up to 75 measurement locations per model and looked at 16 different wind directions at each location. So we took almost 6,000 measurements during the course of this experiment using Cobra probes. So if you're not familiar with our lab, let me introduce you and I'll walk you a little bit about the experimental setup. This is our facility. We're located at the Powell Laboratory at the East Campus of the University of Florida. We don't really view our lab as just a physical testing lab. We do a lot of work on the high performance computing system there. It's really a cyber physical testing facility. In fact, that's very important for this project. So really, it's really the linking of these two things that makes the operation work. But we're really just one program, at least in the US, we're one program of many. And I do want to tip the hat to those other programs. So we work inside of a larger program that's managed by the National Science Foundation. So it's a large facilities program. So if you've heard of, the Large Hadron Collider or the McMurdo Station in Antarctica, or, the LIGO facilities that detected gravitational waves, or more recently the Arecibo telescope, which unfortunately was destroyed but is now being rebuilt. It's this program, which is called the Natural Hazards Engineering Research Infrastructure Program, is sponsored through this effort. And it's actually a broad collection of different programs. There's probably a good chance, if you know an academic here, actually a lot of practitioners too in the US that practice or do research on wind engineering, they're part of this network in some way. There's quite a bit of industry involvement. But just to take a second to acknowledge some of those other groups you can see here, including Florida National University here, also in Florida, of course, that also operates the Wall of Wind as part of that program. So our focus primarily is boundary layer wind tunnel modeling. And for those of you that haven't seen our facility, that's a whole presentation unto itself. But we have some unique features with our terraformer system that allows us to individually change elements. We can change the development section out in 90 seconds to any configuration. And it's all been modeled appropriately. So there's no guesswork in terms of, choosing a roughness length and a geometric scale. We can directly dial that up. So we get to do lots of high throughput testing, but it's a large tunnel, as you can see here. Again, this is just it's a big facility. So I want to immediately point out, as someone who had not done topographic work before, I discovered very quickly I had way more questions, and still have some questions actually, about how we do that maybe even to some extent question, is this really the future of how we're going to do this type of modeling? One of the biggest challenges of doing this type of work is working at these incredibly reduced geometric scales. So we went to 1 to 3,100, which was under the limit in the relevant standards in the literature of 1 to 5,000. But if you look at our Reynolds numbers, we had a rough wall boundary layer, as to be expected. But at the end of the day, the mismatch is a factor of 7,000. It's a huge difference between full scale and model scale. Secondly, because you work in these small scales, when you're trying to take measurements down at the Earth's surface, you're not really measuring in the inertial sublayer or roughness sublayer anymore. You're actually getting into the eddy surface layer. That doesn't really change the mean velocity profile, but it does have an effect on the spectra. As you can see here, the roll off is different. You don't get a 5/3 roll off like you normally would. So that was one thing that we discovered. Working with probes is just a nightmare, to put it in a word. The types of accuracy that you have to achieve to do this, it's incredibly hard. I mean, we have a very large turntable, and we're trying to position the probe within a millimeter, but also too, getting it close to the surface is a challenge. We can only get down to about 8 millimeters before we distort the flow. And there's real consequences. You get easy to break a $10,000 probe moving around, but we did it. Secondly was really figuring out how to get the surface roughness right. As a general rule, the roughness elements on a topo model are going to be disproportionately large to maintain the turbulence. And so we built a calibration ramp. We went through tests for smooth cases up to 5 millimeter ramp cases. Ultimately, we settled on a 3 millimeter terrace height. It probably seems like maybe an unnecessary nuance to bring up in this type of discussion, but in fact, it's a very important one in terms of mechanical turbulence generation over this. We also use 2 different approach flow conditions. Regarding the transitions, one of the other things that we discovered was particularly in places like Puerto Rico and these inland areas like Utuado and Aya Bonito. You know, how do you deal with having, you know, significant topography at the edges of the model? And so we ended up using a tapered type of configuration where we basically introduced a taper like what's shown here at 7 degrees, which generally is accepted. You won't have any kind of boundary layer separation or anything odd happening when you go to that type of increment. So we had these big models, but in the end, we only sampled really in the interior region. So there was plenty of time for the internal boundary layer to build up as it traveled over the region. That being said, we also kept the approach flows dialed in for that particular area. So we did use a marine and an overland condition, where the overland really represented more of the treed type condition. You can see the mean and velocity profiles and turbulence density profiles there. It was quite an operation building these models. It took 150 hours to go from the DEM to the instructions for the 3D router. But then we put them together, and there you can see the instrument gantry on the right. And this is all roboticized. So we built this system. Well, basically everything you've seen we built ourselves, but we built this system to actually move the probe around to do this quickly. So for us, it was really one of our first big major ventures into doing high throughput experimentation in a wind tunnel. Because again, 6,000 measurements over 6 models, it was quite a bit of work. And so we did this. You basically had a sequence, the probe would move around, take measurements, and then we would have to manually adjust the model and then do that for 16 different wind directions. So some of the outcomes of that work, you know, we finished on time. A lot of overtime was spent doing that, but we got the data to ARA. They're able to do it. It did get Peter's modeling did get accepted by the Puerto Rican Building Code, and then also ATC adopted in its hazard locations tool. So, and my understanding, it's currently under consideration for AC 722. Maybe that's passed by now, but we also have a wealth of data. So the issue we ran into at that point is that project was really, it was an applied project. It wasn't a basic science project. So I went to my program officer at NSF and we got some funding to work on this problem. And that's where we began applying machine learning and multi-scale atmospheric simulations. And so I just point out, this is a high risk, high reward project. NSF funds these programs to basically go out and collect preliminary data, try things that would be really hard to get someone to fund you to do through a regular funding channel. But it opened up the opportunity for us to do PIV measurements. And so where we're really headed this work and this stage of the work is we're trying to move away from these probe measurements to getting full, stereoscopic, PIV, and moving away. We already moved past the isolated landforms into the complex topography, but really doing this over a large number of terrain sets. And that hopefully then will help us do the validation for these semi-empirical methods for CFD, numeric weather prediction, and also training machine learning models. And we're doing a lot of that ourselves, which I'll just touch on. So a big focus of the project really is taking the topographic information as inputs to the machine learning model, and then predicting the profile outputs, which is exactly as I've shown here, as well as the numerical weather prediction that Luis is working on. And so, but I have to say my favorite part of this project actually was the fact that this is truly a Puerto Rican project, okay? So the project team is myself, Luis, who's a professor at UPRM, but we also brought in 2 REUs from UPRM, as well as I hired a student from there, Jorge, who's working on the program, and then even another REU from Bucknell who was had family there. But everybody except for myself and the guy on the right was actually in the storm and experienced it firsthand. So it really meant a lot to them to work on this project. I have to speed up here, everyone run out of time, but just some kind of early observations on where this is going. The machine learning prediction is working exceptionally well. So using even shallow networks and training that to the Cobra probe data, we had to do that actually last year first. That's why, because of the pandemic, the lab was shut down. It's worked incredibly well. We're seeing that we can do this quickly. This is just an output here of Humacao, that region, looking at maximum speed up values predicted using machine learning. The whole training on the whole data set, all 6,000 points, and doing this takes about 5 minutes on the laptop that I'm talking to you to do now. So we feel really good about applying this at country scale or even larger. One issue though is we're predicting point speed up, not profiles. And so that's where the PIV system comes in. We're now, we've got the system set up and automated to do PIV data collection. I won't get into all the details here, but one of the things I'm super proud of our team about is they work so hard to decrease the workflow time. And now we're able to do this every 5 minutes. We can do a 15-second scan and get the data up and keep moving. That's light speed at PIV timescales for data collection. But that's the setup. So you can see the 2 cameras. We did have to put 10 seaters upwind to really promote good mixing for that to work well. We have to do a lot of post-processing on the data, more than you normally do, even particularly in a closed circuit tunnel. We're in an open circuit tunnel. We have 8 fans, a lot more vibration. So there's quite a bit done on the image stabilization and pre-processing side, as well as stitching these together. And so this work is still ongoing. In fact, I just got some of the first data last night. Here's a snapshot of some the longitudinal mean velocity profiles over Calabria. This is our smallest area of the bunch. But the goal is to produce about 13 of these transects, with some of them having as many as 15 frames or roughly 9 kilometers. Massive amount of data, 100 plus terabytes of data will be generated off of this, again, which we can use for machine learning. Also, too, concurrently, Luis is working on the numerical weather prediction side. He's using a version of WRF, the advanced research model. He spent a ton of time working on this, getting it down now to 50-meter grid scales. And you can see the model here running. So in the interest of time, I won't get into too much detail here, but you can always turn back to the previous slide and look at it. But now we have a working model, which gives us basically the data that we need in order to do direct comparisons. And so that's where we're headed with this, is using these nested models like you see here. And this is where we can put all the pieces together. So we're looking at the Cobra Pro measurements. We're looking at the PIV. We're looking at the numerical weather prediction modeling. We're looking at using open foam as well. I'm not going to talk about that today. So we're trying to put all the pieces together to look at this now to see what works, what doesn't, and if it doesn't work, why. So that's just one example for in this region. So I'm just going to wrap here to stay within time. Again, this work is ongoing. I gave you a real snapshot of the things that are happening right now. I do have some real questions about the efficacy of boundary layer wind tunnel modeling. I mean, I talked about some of those. The PIV data, I think, is going to be really fascinating to have that. We haven't had that kind of information before. The machine learning approaches really do show early promise. Verdicts out on the NWP using that operationally, but I think on research purposes, it'll work fine. And again, I just want to suggest, if you're interested in this or you want to take part, at UF, we love working with people and bringing people in. So if I've shown you something that would help you, please don't hesitate to reach out. We're happy to share. So let me acknowledge the sponsors, and Chris, I will hand it back to you.
Thank you very much indeed, Forrest. Yeah, I certainly got things I'd like to say on that afterwards. I'm going to give a presentation now. I'm not going to introduce myself. If you wish to know who I am, then I'd point you in the direction of the website. I've introduced myself in a number of presentations beforehand, so I'm not going to do so again. And as I said, because I'm actually giving a presentation, Professor Greg Kopp will actually chair the questions and answers after this session. So if I try to share screen and get the right one. Forrest, could you wave your hand if you can see that, please, just to reassure me? Thank you. My presentation is entitled "The Resilience of Transport and Agricultural Networks to Strong Winds." Essentially, what I want to show today is that once you start talking about spatially distributed structures, the sort of questions asked of wind engineers are really rather different from the ones that are asked for more conventional single point problems. So let's go on. To define where we're at, most of the work in wind engineering, I think, tends to go at the high wind speed level, and this is what Professor Tamura has been talked about, looking at resilience, looking at failure, flying debris and so on, maybe 20 meters a second, something like that, above. A fair bit's gone on at low wind speeds when it comes to pedestrian comfort, pollution dispersion and the like. By contrast, I'm going to talk about the often unregarded middle wind speeds, which are actually very important for the sort of distributed systems I've looked at in my career, agricultural and transport systems, somewhere in that middle range there. And again, Professor Tamura has acknowledged the importance of this. I'm going to first of all look at road networks, then rail networks, then at agricultural networks. Road networks are very basic major effects, such as here on the Spy Bridge, there are a number of roads. The picture quite of the Spy Bridge just shows rather nicely and the standard method of developing wind speed restrictions are to have them staged. So several wind speed levels to close the bridge. And the bridge there that you can see is in Scotland, where I did some work a few years ago. We've also done, to know that, you need to know something about the wind speed that will blow vehicles over. And we've done some work in the past that involved full-scale measurements on real vehicles tied in with wind tunnel measurements and with CFD measurements with some collaborators there. And we can come up with curves that look like the curve at the top there that show the wind angle against the rolling moment on the vehicle. And there's lots of data on that curve for lots of vehicles. And we can use that in a number of situations, such as on the bridge there, or another area where we did work was on the wind around the base of a very high-rise building in a city in the north of England, where vehicles blew over. And we can derive something I think wind engineers are comfortable with, a plot of wind speed against wind direction at which vehicles blow over. We're happy enough with that, really. And we can begin to use that to develop criteria, such as I put a collation of criteria here for a whole load of bridges in the United Kingdom that shows several different levels at which you would restrict vehicle movement. A low level maybe for high-sided vehicles, a higher level for ordinary cars. Okay, that's okay. And we can again derive wind speed criteria, vehicle speed in miles an hour, and I'm afraid most people in the UK do still use miles an hour for vehicle speed, against accident wind speed, gust wind speed, again in miles an hour, and we can devise wind restrictions for different sorts of vehicles. The interesting thing is, of course, is that what is regarded as a failure wind speed varies with the nature of the operation, with what speed the vehicles are going, which is different from building aerodynamics. You just end up with one failure wind speed. Rail networks are both similar and different. Trains do blow over, and containers blow off trains. Trees fall on railway lines, and Professor Tamura showed pictures of bouncy castles flying in the air, and that happens a lot on UK railways, with trampolines landing on railway lines and causing disruption. Again, we can do something very similar. You look at the top right left-hand picture, that is actually our main to actually get the, I need to stop that, to actually get the right relative movement between train and ground and train and air, you actually need to fire the train along a long test track, and that's a very large facility, 200-meter long test track that University of Birmingham has. And again, we can get curves that look like that show the force coefficients against the wind angle. And we can use those to get what are known in railway terms as crosswind characteristics. So again, a plot of vehicle speed against accident wind speed for different wind directions. Or we can plot that in terms of overall risk. Again, wind engineers are fairly happy with that sort of thing, I think. But it's not quite so simple. When it comes down to operations, you suddenly find you've got all sorts of other things involved, like trampolines landing on the track, like trees blowing onto the track. When you want to impose speed restrictions, you suddenly find that to enable those to be rolled out over the entire network during the course of a day, a decision has to be made about 3 o'clock in the morning to be able to make those wind speed restrictions. So again, wind engineering is simple enough, but trying to match them with these operational criteria is actually far from simple. I just want to stop this to say what we're looking at here. What I'm going to show is a picture of a storm moving across Britain, and we'll see an incident occurs somewhere in the middle of Britain. This is actually a flooding incident on the railways, not wind, I'm afraid. And then we'll see lots of dots spreading out from that incident that show the amount of delay, what we call delay minutes, that were measured over the course of the day. So we see the storm coming across at 11:30 in the morning there. And as it moves across, you can see the incident occurring there at that point, and then you can see the delays spreading out across the country. You can see them there. And you can see one incident at 11:30 in the morning is still having effects at 8 o'clock at night, 9:30 at night, and it reaches from the south coast up to Edinburgh in Scotland. Local effects can have system-wide significance. So the questions in transport system terms, what are safe wind speeds for road and rail vehicles? Well, we're comfortable with that as wind engineers. We can probably answer that. We've got the tools. But what are those risks of those wind speed, gust speeds being exceeded? And that means we need to do some sort of convolution of mean and gust probability distributions, which you don't often do. How often do these wind speeds occur? If you close a bridge at a certain average wind speed, how often is that bridge going to be shut during the course of a year? That's a profoundly political point and can have all sorts of societal effects. How quickly do these dangerous storms develop and subside? What are the resilient operational wind speeds that allow for things like flying trampolines? What are the temporal and spatial extent of these high wind speeds? These questions in red are questions that wind engineers don't always ask. It's actually quite difficult in some ways to get a handle on them, to be honest. Let's look briefly at agricultural systems. This is one of the areas of work that we've been involved in over the years. And the work that we've been looking at is what's known as the lodging of various sorts of crops, flattening of crops due to high winds. And there's work going on in the US on looking at tornadoes in lodging as well. And we've developed a mathematical model of the lodging process. We've made various field measurements, looked at the displacement of crops in high winds, and we've managed to come up with fairly simple formulae I'm not going into this now, that relate the lodging wind speeds to the dynamic parameters of the crops and also to the agronomic parameters, how tall, how big the root is. And so, again, we can get a handle on the wind speeds that cause these crops to overturn. What are the lodging wind speeds? And that we can actually then use to talk to crop breeders to say, okay, you need to increase the lodging wind speeds by, say, making the root plate bigger or something like that. Fairly happy with that. But then also questions that wind engineers don't so often answer. What are the risks of those wind speeds being exceeded again? That requires some sort of convolution of mean and gust probability distributions. What is the spatial and temporal extent of those wind speeds? So there are some questions. Briefly, very briefly now, what might be the answers to those questions? Well, you can convolute mean and gust wind probability wind speeds. I don't often see it done, but if we begin with a viable distribution, look at fluctuations around a mean, empirically, you can show that the gusts are given by a modified viable distribution where the K parameter is actually a function of the turbulence intensity. It's quite convenient there. So we can do that. And we've used that sort of approach in looking at risk calculations for a new high-speed rail line that's being built in Britain called High Speed 2 from London to the north. And we've done various risk calculations that have identified hotspots along the railway line where we're going to need wind fences. Very much ongoing work at this point. Then we get on to another question. How often do gust wind speeds of different levels occur for a fixed mean wind speed? Say if we have a control on a bridge where the wind speed, where the vehicles are stopped if the mean wind speed exceeds 50 miles an hour, how often a gust wind speed is going to be exceeded on that? And there, again, it's not a question we've asked very often. It turns things around a little. And we've done a bit of work looking at some basic data to try and get a handle on how often the number of standard deviations above a mean is exceeded by 1 second gusts, 3 second gusts, and so on. I can talk to people about that if they're interested. When it comes to the specification of spatially and temporally varying wind speeds, you can use various methods. There are some things in the UK and I guess around the world called weather generators that put various climate scenarios in. One of the downsides of these weather generators is they tend to operate over, say, a 10-kilometer or 25-kilometer grid, which is absolutely no use at all if you've got a 100-kilometer motorway and want to know what the weather's doing along there when you haven't got correlated wind. We can look at database integration, look at historic and real-time meteorological records, look at terrain models like Forrest has been looking at, and models of roughness classifications. I'll just briefly mention these. Some colleagues at the University of Birmingham did some work where they looked at treefall on the railway network in a small part of Britain and identified and correlated positions of treefall with positions of potentially high winds. And this is historic data, and we're able to get some sort of handle on where the sensitive sites were. Colleagues at another university, the University of Lancaster, have developed a model called TREEFALL, tree risk evaluation. What sort of wind speeds are trees in danger of falling? And there they put together all sorts of wind speed averages, a terrain model, FlowStar they use, surface roughnesses, to actually provide information of where trees are at risk. And that can be used in all sorts of ways, including going and felling trees at sensitive sites. And they more recently adopted this to look at crop lodging as well, crop blowing over. So a very quick round through, but some concluding remarks. The resilience of transport and agricultural systems, it forces us to ask questions of wind engineers that are different from those we normally ask. How often are gust wind speeds at a certain level exceeded, given a particular mean wind speed, for example? What is the spatial or temporal extent of windstorms? A particular windstorm, what does it look like? How big is it? And that's important for long, thin systems. operational realities, whether we like it or not, often result in suboptimal procedures. And local events can have a system-wide significance. So I'm going to end it there, folks. I think I've had my share of time. And if I could ask Professor Koch to show himself and guide us through the questions. As my colleagues ask questions, if they could put themselves on video so people can see them. Thank you very much indeed.
Well, thank you, Chris, and thank you also from the larger wind engineering community for organizing these lecture series for us. I know I've personally enjoyed them, even though they're often very early in the morning for me in Canada here. It's a great way to start the day and to see familiar faces and talk about the topics that we love. When I first saw the schedule for this one with 3 very different talks, I was kind of confused because I thought, wow, those are 3 very different talks. But I think the common theme that I was seeing here is that as a discipline, we need to start asking some different questions if we're going to mitigate disasters and reduce losses. And there's some really interesting problems that are coming out and some interesting questions that can be raised. We won't be able to get to all the questions today, and the panelists will provide responses that will go later with the seminar links that Professor Baker will send out. The first question is for Professor Tamura, and I'll also ask the other panelists to weigh in if they want to, following his response. It started with the point about temporary structures and the problem of design life and design load levels, and there's cost associated with this, and so you can see this also with tornadoes, for example, where the probability of an individual structure being hit is small, but communities get hit every year, and so you have this this challenge of designing for mitigation of losses versus the individual structure which individual owners have to pay for. And the question for Professor Tamura is, how might you pay or persuade owners to do this? How might you persuade code committees to change design practice for that kind of thing?
Yes, and very good question. So in some cases, we should pay more. And it is also true that safety is costly. But so far it is not obligated, but if it is obligated, probably we can find some efficient ways or ideas to reinforce them without spending much money. And also, I said that temporary building, all temporary building, and I didn't say that it should be similar to a general building. So, but construction work office scaffolding should be reconsidered and cannot be said completely temporary, never disappear. It always existing. And so in case of scaffolding, if you remove sheets and nets for strong wind, so you can of course reduce the area, projected area or aerodynamic coefficient. And also if you use only winter, you need not worry about tropical cyclone in summer season or so forth. So so it depending upon the situation, we should appropriately judge the temporary building and the non-temporary building. So it is not always costly, I guess. Yeah. But so my strong question about the construction work office, if you got a job at a construction company, and if you are assigned as a construction engineer, so you should work at the construction work office until your retirement or so forth, so 40 years or so forth. And you do the same thing, drawing, analysis, discussion, taking meals and so forth in that building. So it is similar to the headquarter office, the worker in the headquarter office, working in the very high quality building, but such a construction worker, the same thing they did for almost the same year. So it is unfair and should be reconsidered. Okay.
Thank you. Do the other panelists want to add anything to that? Your experiences? Yeah. Okay. Next question from the chat box is for Professor Baker from Tengwu. Thank you for your nice presentation. During a strong wind event, such as a hurricane, do we have a good approach, say beyond the kind of empirical strategies to make a decision for transportation network operation to balance mobility and loss? Both probability contribute to resilience of a community or region.
I think simple answer is probably no in UK terms. We don't have a very good approach. It is very much the decision. I can only speak for the UK, but the decision structure is very diffuse. For transportation systems, there are, in the rail system, there are a number of companies involved. In the road system, roads tend to be looked after by the local government units. And so each might have their own procedure. These very rarely tie up with one another. And they're very much based upon experience. I think there's a whole set of issues here about which I don't claim to know the answer to, about how we analyze complete systems in terms of risk and yet bring that down to local restrictions. I think there's some real academic work to be done here that will then need translating into something that is usable. At the moment, it is very empirical and very ad hoc, and people go by their own experience.
Thanks, Chris. Next, we have a couple questions for Forrest. Thank you for an interesting presentation. Could you talk about the role of machine learning in the PIV tests, and how would machine learning help with PIV from wind tunnel data?
So presently, the machine learning really won't help us, collect the data or do the processing. Now, in the future, I think that could change. How we're using machine learning is we're collecting data and we're training a model, which we hope, we have a robust training set. So then now we can apply that model to any type of terrain. And so we're doing this with the wind tunnel experiments. But there's hope to do that in other types of environments. You could do the same thing using a CFD output, for example. But we're hoping to show some preliminary proof of concept with that. And then we can begin looking at the nuances of the problem. For example, trying to figure out not only are you dealing with topography, but how do you address the terrain issue? Where machine learning could, I think, play a huge role. And I think that, Greg, this speaks to your first comments. Where I think the state of engineering is right now, and this isn't just wind, is we're all in a process of retooling and upskilling. And this, particularly for the younger crew that's listening to guys like us talk right now, pay close attention, because there's a big opportunity for you. The world is moving into, for example, a heterogeneous computing environment now. And I made a comment on my last slide, and I wish I'd actually called that out. We're moving away from traditional computing, like, running something on your laptop, using GPUs and FPGAs, things like that to actually speed it up. So you think about a PIV experiment, they're a total pain in the butt to run. I mean, it takes so much work